we've talked about that the derivative of sine of x is equal to cosine of x, and that the derivative of cosine of x is equal to negative sine of x. I believe we've shown this graphically. Definitely something you want to take to heart. Today, after we talk about the quotient rule real quick, we will use these derivatives to also find the derivatives of the rest of the trigonometric functions. What I want to do before we do that is I actually want to show you how to find the derivative of either one of these using the limit definition. But to do that, we need two things, which we've talked about already. We need the fact that the limit as x goes to 0. Actually, I'm going to use a different one. I'm going to use theta of sine of theta over theta is equal to 1. Right? It doesn't matter what theta is. It could be x, sine of x over x, or sine of q over q, or sine of anything over anything, as long as the anything is going to 0. We also have another one. The limit as theta goes to 0 of 1 minus cosine of theta over theta is equal to 0. And I'm pretty sure we talked about this before, but if you guys want, I can show you this again. Let me know if that's something you want. And I believe the one we're actually going to use is not that, but it's slightly different than that. It's the fact that the limit as theta goes to 0 of cosine of theta minus 1 over theta is also 0. And the way we can justify that is by saying, well, look, if this is 0, I'm going to multiply this by negative 1, or really factor out a negative 1. So I can say this is the limit as theta goes to 0 of negative 1 times 1 minus cosine theta all over theta. Hopefully you guys can see that that's true. If I multiply the negative 1 through, I can multiply it. It's really negative 1 over 1. The negative 1 times 1 is negative 1, and the negative 1 times negative cosine is positive cosine. So this is the same as that, but I can factor the negative 1 out. Say, oh, that's negative 1 times the limit as theta goes to 0 of 1 minus cosine of theta over theta. But we already know that this is 0, and negative 1 times 0 is still 0. So these are the two limits we need to use the limit definition for the derivative of either sine or cosine. Doesn't matter which one we do. I feel like I might have done sine before. It's hard for me to remember. I know I did it in one of the classes. It might have been this one. Let's do cosine. And again, please do let me know if you have any questions about either one of these limits. Hopefully this one's like, oh yeah, we totally know that one. This one I can see maybe not remembering quite as well. So I want to find the derivative of cosine of x using the limit definition of the derivative. And to do that, we're going to start with the limit definition, right? We're going to say, oh yeah, the derivative of a function, right? If I want to think of this as f of x, the derivative of f of x is equal to the limit as h goes to 0 of f of x plus h, whatever that is, minus f of x, whatever that is, all over h. F of x plus h is cosine of x plus h. And f of x is cosine of x, all over h. Any questions about this so far? Seeing the limit as h goes to 0 of cosine of x plus h minus cosine of x over h. But now we're going to run into a problem. The problem is there's not really a good way to combine these, right? When you subtract sines or cosines, or really any kind of functions, right? If you're adding, subtracting functions, typically there isn't a good way to do that. Just like you can't do anything meaningful with this, right? Square root of x plus h minus square root of x. There's nothing to be done there other than multiply by the conjugate. That's not what we're going to do here, but the idea is kind of similar in that we have to use something. And something here is to use one of the trig identities. So there are two angle sum-identities that I'm going to show on the other side. The one you need for the sine, for the derivative of sine, is that sine of A plus B is equal to sine A cosine B plus sine B cosine A. Whereas the cosine one, cosine of A plus B is equal to cosine A times cosine B minus sine A times sine B. And I'll just point out, since we're here already, that if it's sine of A minus B, then it's this minus this. And if it's cosine of A minus B, then it's this plus this. So for the sine function, whatever the addition or subtraction is here, it's the same addition or subtraction there. For cosine, if it's addition or subtraction here, it's the opposite subtraction or addition over there. Now we use this one. Cosine of A plus B, or in my case, cosine of X plus H, is equal to cosine X times cosine H minus sine X times sine H. So this is equal to the limit, as H goes to 0, of cosine of X times cosine of H minus sine of X times sine of H minus cosine of X all over H. Now we're thinking, well, great, what do we do with that? Well, I do see that I have a cosine here of X and a cosine of X here. So I'm going to put these two parts together. I'm going to make this actually into two different fractions. I'm going to write this as the limit as H goes to 0 of this minus this all over H. So cosine of X times cosine of H minus cosine of X all over H. And then this part here, the sine X sine H all over H. Now we're going to do some factoring. So from these two pieces, the reason I put these two pieces together is so that I could factor out the cosine of X. So I'm going to rewrite this. Do I have enough room over here? Maybe. No, I probably don't. I'm going to rewrite this as the limit as H goes to 0. I'm going to factor out the cosine of X. When I do that, I'm left with cosine of H minus 1 all over H. And I could write this as, I could write the whole thing over H, but really I want this piece kind of by itself. So cosine of X times, or if you want, cosine of X over 1, if that is a little bit clearer what's happening. In a similar way here, I'm not so much going to factor out, is just rewrite it as minus sine of X over 1, if you like, times sine of H over H. Normally I would just jump to the conclusion, but I'm going to do one more step. So I'm going to write this as, so again, when you have a limit of something minus something else, you can write it as the limit of this minus the limit of that. And then if you have a limit of a product, you can write it as the product of the limits. So I'm actually going to write this as 4 limits. I'm going to write this as the limit as H goes to 0 of cosine of X times the limit as H goes to 0 of cosine of H minus 1 all over H minus the limit as H goes to 0 of sine of X, I'm dropping the over 1, times the limit as H goes to 0 of sine of H over H. Okay, I'm going to ask for you guys to help me. Either you can say words or type things in the chat. What is the limit as H goes to 0 of cosine of X?
1.
If it was cosine of H, it would definitely be 1, because cosine of 0 is 1. But I'm not plugging in H, I'm not plugging in X equal to 0, I'm plugging in H equal to 0. There's nowhere for H to go. So what am I left with?
Cosine.
Cosine of X. So yeah, so right here, I'm just going to get cosine of X times, now what's the limit as H goes to 0 of cosine of H minus 1 all over H?
0.
Yeah, right? We did that on the other side. Oh yeah, that's 0. Minus the limit is, so okay, so this is similar to the first one. What's the limit as H goes to 0 of sine of X? I see someone has already answered. It is definitely sine of X times The limit as h goes to 0 of sine of h over h is?
1.
Thank you. Appreciate the people talking. So look, I get cosine of x times 0 minus sine of x times 1, which is minus sine of x. So we actually have proved, using the limit definition of the derivative, that the derivative of cosine is equal to negative sine of x. Pretty cool. You can do the same sort of thing for the sine function. The only difference is when you get to this stage where you're doing sine of x plus h minus sine of x all over h, instead of using the identity for cosine, you would use the identity for sine. So that's pretty much it. Okay, so sorry, let me grab the, where'd you go? Problems I wanted. Sorry, that's a whole bunch. Okay, cool. Okay. So just as a reminder, here are a few derivatives we have. We have the derivative of sine of x is cosine of x. We have that the derivative of cosine of x is negative sine of x. We have that the derivative of e to the x is e to the x. We have that the derivative of x to a power is equal to 1, that power times x to the 1 less power. We also have the product rule, which we talked about last time. You take the derivative of f times g, it's equal to f prime g plus f g prime. And then I don't think we talked about it last time, but I imagine you talked about it in your classes. You also have the quotient rule, which is that the derivative of f divided by g is very similar to the product rule in the numerator. It's just the same thing, but with subtraction. It's f prime g minus f g prime all over g squared. I usually say this in my head as the bottom function times the derivative of the top minus the top function times the derivative of the bottom all over the bottom squared. Some people say this other thing where they say it's low d high minus high d low all over low squared. So let's do some practice. Let's use the quotient rule. Well, actually, before we use the quotient rule, there's one other thing I want to mention. There's one other rule that kind of gets caught up for people with lives. So the constant multiple rule. So if you have the derivative of just a constant, it's 0. For example, the derivative of 5 is 0. And I would encourage you to think about it in the way, oh yeah, I know that y equals 5, right? The function, the graph y equals 5 is a horizontal line. And the derivative, aka the slope of the line, or the slope of the tangent, is just 0. So constants have a slope of 0, their derivative is 0. On the other hand, if you have a constant times a function, its derivative is going to be the constant times the derivative of that function. So you write it as c times f prime of x, you write it as c times the derivative of f of x. Either way. But for example, the derivative of, say, 6 times x to the second, we know is 12x, but really it's 6 times 2x, which is 12x. And the reason I point this out is because there are definitely some questions on the homework. People were asking about where you have a lot of variables happening. For example, I think someone asked me something similar to this. So I want to find the derivative with respect to x. I'm going to change this up just a little bit. Ax over k squared plus, what do I got there? Sorry, it's hard to see all the things. Plus kx cubed. And so this can be a little confusing because there's all these letters. But here's what we have to remember. X is the variable. A and k are constants. And so if I was doing this question, what I would actually do before I started differentiating is I would rewrite it just slightly. I would rewrite this as So I'm going to write the constant times the variable. I'm going to write ax over k squared as a over k squared times x. And k times x cubed is already kind of written that way. And now when I take the derivative of a constant times a function, the constant hangs out. And I multiply it by the derivative of the function. The derivative of x is just 1. In the same sort of way here, the constant multiple k just hangs out. And I multiply it by the derivative of the function. And the derivative of x cubed is 3x squared. And then we could simplify this a little bit. I would probably rewrite this as a over k squared plus 3kx squared. So when you have variables that are letters, we have to remember that they are, when you have constants that are letters, you have to remember that they're not variables and we don't take the derivative. So another example of this would be something like the derivative with respect to x of a to the 9th plus a to the 4th times x to the 5th plus x to the 9th over a squared plus, x to the, a cubed over x cubed. And so if I was going to differentiate this, this is where they're trying to trick you, right? They're trying to make you think, oh, a to the 9th, I might think the derivative is 9a to the 8th, but it's not. The derivative is 0, because the only thing that's a variable in this expression is x. Right? If I say derivative with respect to x, I'm treating every other non-x thing like a constant. So the derivative of a to the 9th is 0. The derivative of a to the 4th times x to the 5th is a to the 4th times 5x to the 4th. The derivative of x to the 9th over a squared is 9x to the 8th over a squared. Because really I'm thinking of this as 1 over a squared times x to the 9th, and the derivative is 1 over a squared times 9x to the 8th. And finally, this one, I do have to think about rewriting it for a second. I know that that part is a cubed times x to the negative 3rd. So its derivative is a cubed times negative 3x to the negative 4th. And then you could simplify a tiny bit. This would be 5a to the 4th x to the 4th plus 9x to the 8th over a squared minus 3a cubed. You can write it as a cubed times x to the negative 4th, or you can write it as a cubed over x to the positive 4th. Either way is fine. So that's how I would tackle a problem like that. Again, you really have to make yourself think, okay, constants on their own have a derivative that's 0. Constant multiples of variables hang out and multiply the derivative of the variable part. Okay. I didn't really want to erase this yet. So let's talk quotient rule. So for the quotient rule, we can take all sorts of derivatives, like the derivative of, I don't know, e to the x over sine of x. And really, I mean, part of this is just making the rule something that you memorize. Yes, you could look at the quotient rule to your heart's content. Eventually, you're just going to do it enough that you're like, oh yeah, I remember how it goes. So the derivative here, and here's really the way I think about it. It's the bottom times the derivative of the top, and the derivative of dx is just e to the x, minus the top times the derivative of the bottom. The derivative of the bottom is cosine of x, all over the denominator squared. And usually I would probably leave this unsimplified. In this case, it's fairly easy to factor out an e to the x. So we probably would factor out an e to the x, right? It's e to the x times sine x minus cosine x, all over sine squared x. But I'm usually not trying to do a whole lot of simplifying with my quotient rule unless I'm specifically trying to do something with it. So let's look at a couple more examples. How about the derivative of, what have I got next? Sure. X cubed over x squared plus 1. Well, again, we're just throwing the rule at it. I want to emphasize, so some people really get stuck in this way thinking, oh, it's f prime g minus g prime f all over g squared. The order of multiplication doesn't matter, right? You can say f prime times g or g times f prime. It's the same thing. So I usually say it as g, or the bottom, times f prime, or the derivative of the top, minus the top, or f, times the derivative of the bottom, or g prime, all over bottom squared. In case you're like, where is he getting these f's and g's from? I'm making the natural kind of, I'm assigning the names to the top and bottom of this expression. I'm calling the top part f and the bottom part g. And so usually I might multiply. No, I'm really like not trying to simplify this at all, but I guess we could. This one simplifies as 3x to the fourth plus 3x squared minus 2x to the fourth over x squared plus 1 squared. And then you could, I guess, you could simplify this as x to the fourth minus plus 3x squared all over x squared plus 1. Simplifying is not really the point at this stage. But what I do want to show you is, what if we go the other way? What if we find the derivative of, instead of this, the reciprocal, x squared plus 1 over x cubed? We could certainly use the quotient rule here. But can we go over how to find horizontal tangent lines? For sure. In fact, we'll come back to, we'll look at both of these and talk about how we can find a horizontal tangent line for them. Excellent question. That one, yeah, that one. Okay. So in this case, the derivative, instead of using the quotient rule, if you have a quotient where you have all like powers of x and only one term in the denominator, we can instead just divide each thing by x cubed. I can write this as the derivative of x squared over x cubed plus 1 over x cubed, which is the derivative of 1 over x, or x to the minus first, plus x to the minus third. And that's equal to negative 1 x to the minus second minus 3 x to the minus fourth. And you could leave it like that, or you could write it as negative 1 over x squared minus 3 over x to the fourth. Very, very different answer than the other one. So what I'm trying to point out, some people think like, oh, if you flip the function, you flip the derivative. That's not the case, right? If you flip the function, it's a totally different derivative. But Michaela asks rightly, how about how to find where we have a horizontal tangent line? So let's actually look at this one. So I want to know, where does this function, so where does y equal to x cubed over x squared plus 1 have a horizontal tangent? So if we're asking the question, where does this thing have a horizontal tangent, we're really asking the question, where is the derivative equal to what?
0.
Yeah, exactly. So the idea there is that we want to take our derivative and set it equal to 0 and solve for x. So I'm going to set my derivative, which is x to the fourth plus 3x squared over x squared plus 1 squared equal to 0. And typically, if it's a quotient like this, my first step is typically to multiply both sides by the denominator. So I would probably rewrite this automatically as x to the fourth plus 3x squared, right? Multiplying both sides of x squared plus 1 squared equal to 0. Right? So you multiply the left by that, you get the top. If you multiply 0 by anything, you still get 0. And then I would factor. I can factor out x squared. So you get x squared times x squared plus 3 equals 0. So I either get x equal to 0, right? I set x squared equal to 0. I get x equal to 0. Or I set x squared plus 3 equal to 0, which doesn't have any real solutions, right? Because if I set that equal to 0, I get x squared equal to negative 3 but a real number squared can't be negative. So for this particular function, y equal to x cubed over x squared plus 1, we have a horizontal asymptote when x is equal to 0. I should say, not a horizontal asymptote, a horizontal tangent line. Sorry about that. Let's look at another example.
I had a quick question about that one real quick.
Sure.
How did the x to the 4th plus 3x squared stay the same when you multiplied it by the denominator?
Well, it's not, I didn't multiply that by the denominator, I multiplied this by the denominator. So I've got x squared plus 1 squared times x to the 4th plus 3x squared over x squared plus 1 squared equals to 0 times x squared plus 1 squared. And so on the left side, those just cancel out. Oh, sorry, this way.
Yeah. Okay, thank you.
And just to kind of expand on this point a little bit, because it is worth noting, whenever you're setting a quotient equal to 0, you end up just setting the top equal to 0, right? Because you multiply both sides of the denominator. On the left side, you just get the numerator. On the right side, you still get 0. And so what I always say to myself, oh, how can a fraction equal 0? Well, a fraction can only ever equal 0 if the numerator is equal to 0 and the denominator.
Okay, thank you.
You're welcome. Yeah, but I mean, it's a good point. Like, yeah, I was going to say that whether or not you ask that question. Like, I think it's a good thing to know. You can always just jump to saying, oh yeah, I'm just going to set the top equal to 0 and solve that. So let's do another one, because I think this is definitely something you're going to spend time doing in the future. So let's talk about one or two more examples. Yeah, I've got one or two more examples that I think are worthwhile. Let me go back actually for a second, because I'm pretty sure there's one I want to do. Are you not on this page? Sorry. I thought you were there. One sec. Nope, that's not the one I wanted. Fine, I'll do it myself. Okay, so let's say I want to, let's do this one. So we'll ask the same question for the next two problems. So I want to find all horizontal tangents, find all. I should say find all values of x where there is a horizontal tangent. So find all values of x. Okay, for the following function, for f of x, we're just going to do one because I forgot there's another rule we need before I can do that. Let's look at f of x equal to, sure, x squared over x minus 1. Fairly straightforward looking function. Let's figure out where we've got some horizontal tangent lines. So I'm going to take the derivative. It's going to be the bottom times the derivative of the top, which is 2x, minus the top times the derivative of the bottom, which is 1, all over the bottom squared. And now I want to set that equal to 0. And really, so when you're setting derivatives equal to 0 like this, we definitely have to simplify. So I'm going to simplify the top part here. So this is going to be, let's see, 2x times x and 2x times minus 1. It's going to be 2x squared minus 2x minus x squared times 1 is minus x squared. And I could write over x minus 1 squared equals 0. But I know really I just have to set the top equal to 0. Because again, I can multiply. In fact, I will multiply both sides by x minus 1 squared. So on the left side, oh yeah, the thing I multiply by cancels with the denominator. That's why we multiply by it, right? Because we want to cancel out the denominator. And then on the right-hand side, you just get 0. So look what I've got. I've got 2x squared minus 2x minus x squared. So I'm going to put the x squared terms together. 2x squared minus x squared is just x squared. X squared minus 2x equals 0. I'm going to factor out an x. So x times x minus 2 equals 0. So in this case, I get x equal to 0 and x equal to 2. That's where this particular function, x squared over x minus 1, would have horizontal tangent lines. And here's what it looks like in case you're curious. The graph of this has a vertical asymptote at 1 There's also a slight asymptote. I'm not worried about it. But it does this kind of deal. Sure. So it has a horizontal tangent right there at the origin. And then there's also, right here at the point 2, 4, there's another horizontal tangent right there. So that's what we are getting when we find those points. We're saying, oh yeah, that's really, you're finding a lot of the times where the function either has a local maximum, right? That point is bigger than all the stuff next to it, or a local minimum. That point is smaller than all the stuff next to it. So I do think we should talk about, yeah. So quotient rule. Go ahead. Sorry, say that again.
I have a quick question about the previous problem.
Okay, sure. One sec.
Oh, what happened to the 2x squared? Oh wait, never mind. You subtracted, right?
Yes.
Okay, never mind.
Good. It's good to ask questions. So the thing we often use the quotient rule for, well, I mean, the thing we use it mostly for is to take a lot of derivatives, but we also use the quotient rule to take the derivative of the rest of the trig functions. So if I wanted to find, say, the derivative of tangent, I will be perfectly honest. I have never used the limit definition of the derivative to find the derivative of tangent. I imagine it's doable. It sounds like a giant pain in the butt. I know there's like an identity for tangent of a plus b. It's gross. And it's not the way I've ever seen anyone ever do it in their life. The way we do the derivative of tangent is we write it as the derivative of sine of x over cosine of x. And then we use the quotient rule. And say, okay, well, that's going to be the bottom, which is cosine of x, times the derivative of the top, and the derivative of sine is cosine of x, minus the top, which is sine of x, times the derivative of the bottom, which is negative cosine of x. Sorry, derivative of the bottom is cosine of x, the derivative of cosine is negative sine of x. All divided by the bottom squared. And then we simplify it. So here's the thing. The numerator, so cosine times cosine is cosine squared. So it's going to be cosine squared of x. And minus sine of x times minus sine of x is plus sine squared of x. And in the denominator, we have cosine squared of x. And I imagine you guys probably know that cosine squared x plus sine squared x is always equal to what?
1.
Yeah, exactly. Sorry, everyone's favorite trig identity. Sine squared plus cosine squared equals 1. Or cosine squared plus sine squared equals 1. And then instead of writing this as 1 over cosine squared, I'm going to write it as 1 over cosine squared, which is 1 over cosine is really secant. So write this as secant x squared or secant squared of x. So the derivative of tangent of x is secant squared of x. You definitely want to memorize that. And you're definitely going to memorize the other ones that we're going to talk about right now. So the nice thing is the rest of them pretty much work out in a very, very similar way. Let's do the derivative of cotangent. So the derivative of cotangent of x, well, tangent is sine over cosine. What's cotangent?
Cosine over sine x.
Yeah. And then same idea. We're going to do, okay, the derivative using the quotient rule is the bottom sine of x times the derivative of the top, and the derivative of cosine is negative sine of x. I should always say the of x, right? Because it's always cosine of a thing or sine of a thing. There isn't, you can't just write like cosine and call it a day. There has to be cosine of something. Sorry. So then minus, so we did the bottom times the derivative of the top, minus the top, which is cosine of x, times the derivative of the bottom, which is cosine of x, all over the denominator squared, which is sine squared of x. What's going to happen here is almost the same thing that happened before. But instead of having cosine squared plus sine squared, we have negative sine squared minus cosine squared. So I can write this as negative sine squared x minus cosine squared x all over sine squared x. And then I'm going to factor out a -1 from the top. So it's -1 times sine squared of x plus cosine squared of x all over sine squared of x. And sine squared x plus cosine squared x is 1. So I get -1 times 1 over sine squared. So I get -1 over sine squared x, which is negative cosecant squared of x. And that's the derivative of tangent and cotangent. And I'll say something about this in a second. So these are actually probably the harder two. The last two are even, I think, a little bit easier.
I had a quick question on the last one. How did the sine squared x plus cosine squared x just like go away?
Okay, so that's a trig identity. So let me address that just so everyone's cool.
Okay.
So it really goes back to the unit circle. So good old unit circle has a radius of 1 and has an angle theta. And I call this side x and this side y. And this point here is x comma y. And so if I look at this right triangle, I can see that, oh, sine of theta is equal to the opposite over the hypotenuse, which is y over 1, which is y. And if I look at cosine of theta is the adjacent over the hypotenuse, which is x over 1, which is x. And then I can use the Pythagorean theorem to say, oh, x squared plus y squared equals 1 squared. But x is really cosine and y is really sine. So really I'm saying cosine squared theta plus sine squared theta equals 1. That's where that identity comes from. And that's why it's called a Pythagorean identity, because it literally comes from the Pythagorean theorem.
Okay, thank you. I forgot about that one.
You're welcome. There are other trig identities that come from this as well, but this is kind of the main one. So let's talk about the derivative of secant and cosecant. So the derivative of secant of x, so just like for tangent and for cotangent, we're going to write secant as a quotient. We're going to write it as 1 over cosine. So let's take the derivative. So it's going to be the bottom cosine of x times the derivative of the top, which is 0. So a lot of times I see people say that it's 1, but the derivative of 1 is 0. So make sure that when you're using a quotient rule here and one of the parts is a constant, you're really extra careful about it. They're like, oh yeah, the derivative of 1, that's 0. Minus the top, which is 1, times the derivative of the bottom, and the derivative of cosine is negative sine of x. All over the denominator squared, which is cosine squared of x. And then, so I get 0 here, minus a minus is plus sine. So I get sine of x over cosine squared of x. And while this is technically correct, nobody writes it this way. So what we do instead is we rewrite this as, well, sine over cosine squared, I can rewrite as 1 over cosine of x times sine of x over cosine of x. Still the same, right? I multiply it out, 1 times sine is sine, cosine times cosine is cosine squared. And that's equal to, well, 1 over cosine is another name for secant. And sine over cosine is another name for tangent. So the derivative of secant of x is secant x times tangent x. And now here's what I'm going to say, because I think there's a nice kind of correspondence here. Let me go back to this side for a second. The derivative of tangent is secant squared of x. And then I think about putting essentially a co on each of the functions. So the derivative of tangent is secant squared. The derivative of cotangent is cosecant squared with a negative sign. It totally works. So derivative of tangent is secant squared. Derivative of cotangent is cosecant squared with a minus sign. And it works for secant and cosecant as well. The derivative of secant is secant times tangent. The derivative of cosecant is cosecant times cotangent with a negative sign. I'm still going to show you, but it's kind of nice that you can take these derivatives that are like the nicer ones and slap a co on each of the functions and get the derivative of the other co-function. So the derivative of cosecant of x, we're going to do it the same way. It's the derivative of 1 over sine of x, which is equal to the bottom times the derivative of the top, which is 0 minus the top, times the derivative of sine, which is cosine, all over the denominator squared. I'm going to write my negative cosine x over sine squared x as negative 1 over sine of x times cosine of x over sine of x. And that's going to be negative cosecant of x times cotangent of x, just like we thought it was. So I definitely encourage everyone to memorize the trig derivatives. They come up all the time. They're not going away. I do also, I will say two more things about them. One, I recommend memorizing them in this pattern that I'm about to write down. So I always write them down like this. The derivative of sine is equal to cosine. The derivative of cosine of x is equal to negative sine of x. The derivative of tangent of x is equal to secant squared of x. And we write them in this way, I think, anyway, because sine divided by cosine is equal to tangent, and it's kind of a nice visual reminder of that. And then to the right, we write the derivatives of all the reciprocal functions. So to the right of sine, we're going to write the derivative of cosecant. To the right of cosine, we're going to write the derivative of secant. And to the right of tangent, we're going to write the derivative of cotangent. So the derivative of cosecant of x is negative cosecant x cotangent x. The derivative of secant of x is secant of x times tangent of x. And the derivative of cotangent of x is negative cosecant squared of x. Couple observations. Observation 1. All of the co-functions, cosine, cosecant, cotangent, all have a negative derivative. That is something I always remember. I'm like, oh, it's a co-function. There's a negative sign for the derivative. And then the other thing, I'm just going to say the thing I said before about like, so right, the derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared, right? I'm just putting a co on each of those to get those with a minus sign. Same thing here. The derivative of secant is secant tangent. The derivative of cosecant is cosecant cotangent with a negative. I'm just putting a co on each of those trig functions to get that derivative there with a minus sign. And then the last thing I'll say about these trig derivatives before we move on is something a student showed me one time. This was just a clever way they came up with to remember things. They wrote this. They did tangent x, arrow, secant x, and then an arrow coming in at it with secant x. And they read this as the derivative of tangent is equal to secant times secant. The derivative of secant is equal to secant times tangent. And then they also did one for cosecant and cotangent. They did cotangent of x, arrow, negative cosecant of x, arrow, cosecant of x. The derivative of cotangent of x is negative cosecant x times cosecant x. The derivative of cosecant x is negative cosecant x times cotangent x. So I thought that was like, wow, that's clever. I never would have thought of that, but cool. So whatever works for you, memorize them. You're definitely going to use them enough that you don't want to have to like look them up later on, right? It gets to be like, oh, what's the derivative of this? I don't want to look it up. I just want to know it. Okay. Then we can do all sorts of fun stuff. Like we can say, what's the derivative of tangent of x plus x squared over x cubed minus secant of x? Which isn't particularly terrible, but it's just kind of messy, right? It's the quotient rule again. It's the bottom times the derivative of the top. Okay, the derivative of tangent of x plus x squared is secant squared x plus 2x minus the top tangent of x plus x squared times the derivative of the bottom, which is going to be, okay, 3x squared, and the derivative of secant of x is secant of x times tangent of x, so minus secant of x times tangent of x, all over the denominator squared. And I would definitely not try to simplify this, right? You certainly can, right? It's not terrible to multiply this all out. It's just not really poignant, right? I mean, you can do it, you get some answers, but there's not a ton to be seen there. Let's go ahead and do that. So. Yeah. Let's do that. Sure. I don't want to erase you yet. I just wrote on you. That's fine. You can erase it. Take a picture. Yeah, I was literally just about to go over to the chain rule. Why am I going to do this? So let's think here for a sec. There was one thing I want to say. Sorry, there's an example I have in my head. There's just I want to make sure that I'm not being dumb about it. No, I guess that's fine. Let's find the derivative of x cubed plus 1. Now let's do x to the fourth. Let's do x to the fourth plus 1 cubed. And we're going to do it two ways. First, we're going to just multiply it out. Right? We definitely know how to multiply out something cubed. Right? Remember we were doing it before, we used the Pascal's triangle. When you multiply out something cubed, it's going to be the first thing cubed. So x to the fourth cubed plus 3 times the first thing squared times the second thing to the first plus 3 times the first thing to the first times the second thing squared plus 1 times the second thing cubed. So simplifying this before I differentiate, I get the derivative of x to the 12th plus 3 times x to the fourth squared is x to the 8th. Plus 3 times x to the fourth plus 1. Now we take the derivative here. Derivative of x to the 12th is 12x to the 8th. Derivative of 3x to the 8th is 24x to the 7th. And the derivative of 3x to the fourth is 12x cubed. Okay, but now I want to think about more generally, and I'm going to come back to this, so don't worry. The idea I really kind of want to emphasize here is that my outer function here, the thing that's happening kind of last, is them cubing something, right? I've got something cubed. And I know that the derivative of x cubed is 3x squared. And so my idea here, my thought process is, oh, well, I've got something cubed. I think its derivative is 3 times that something squared. it's not exactly right, but it's mostly right. I'm just missing a little bit. And so to see what we're missing, let's actually factor this so it looks like that. So let's see, I can definitely factor out a 12x cubed, right? Because I've got x cubed in each of the x. So factor out a 12x cubed. 12x cubed? I feel like I made a mistake. Oh, I did. I made a huge mistake. You guys let me get away with murder, practically. What?
The 8's supposed to be an 11.
Yeah.
I was gonna say I didn't know if I like missed something.
You should definitely speak up. I definitely make mistakes. That one was not on purpose. Something to like, I'm gonna make a mistake on purpose. What am I doing? This one was a total accident. Yeah. So yes. You guys let me get away with all kinds of things. So still factoring out 12x cubed though. And now I'm left with x to the 8th plus 2x to the 4th plus 1. And this factors as x to the 4th plus 1 quantity squared. So I've almost got, in fact, I've pretty much got that, except I only want a 3 there. So I'm going to write this 12x cubed as 3 times 4x cubed. So this is 3 times 4x cubed times x to the 4th plus 1 squared. Or as I'm going to write it again, 3, I'm just changing the order of multiplication. 3 times x to the 4th plus 1 squared times 4x cubed. And so look, I kind of got what I thought I was going to get, except I was missing this n factor of 4x cubed here. Which you might notice is exactly the derivative of x to the 4th plus 1. So the idea behind the chain rule here is that when you take the derivative of something to a power, you take the derivative of the outside function. So like something to a power is 3 times my something to the 1 less power times the derivative of the insides. And more generally, the idea of the chain rule is that we're going to differentiate the outer function. We're going to leave the insides alone, and then we're going to multiply by the derivative of the inside. That's always how I'm going to say it. Let's look at a couple more examples. Actually, yeah, let me write down. So some books, I think your book, start off with kind of a lesser version of the chain rule first, which is the power rule version of the chain rule, which is that if you have the derivative of f of x to some power, it's equal to n times f of x to the 1 less power, just like we did before, but then you have to multiply by f prime of x. That's the power rule version of the chain rule. You don't really need to memorize this because we're going to talk about the larger version of it shortly here, but I mean, it's certainly not bad to memorize that. So for example, if I want to take the derivative of, I don't know, x to the 7th plus tangent of x to the 19th power, the way I really say it in my head is I've got some stuff to the 19th power. And the derivative of x to the 19th is 19 times x to the 18th. So the derivative of some stuff to the 19th power is 19 times my stuff to the 18th times the derivative of my stuff. That's what I'm thinking. I'm like, oh, I do the derivative of the outside function. The derivative of something to the 19th is 19 times something to the 18th. And leave the something the same as it was before. But then after I do the derivative of the outer function, leaving the insides alone, I then have to multiply by the derivative of the insides. And the derivative of x to the 7th plus tangent of x is 7x to the 6th plus secant squared of x. Do something quick here. Sorry, one sec. Let me just grab a picture of all you attendants. So many of you. It's good. I'm glad there's so many of you. It's good to see all your pictures and or faces and stuff. And so this is kind of the real idea. I mean, there's not much more to say about this further, right? I mean, we could do something like the derivative of, I don't know, other fun trig functions, 2x cubed plus cosine of x minus cosecant of x to the 9th. And the derivative is going to be, well, I've got some stuff to the 9th. My derivative is 9 times my stuff to the 8th times the derivative of that stuff. So let's see, it's going to be 9 times all this left alone. It's really, really important. I've definitely seen people in the past make the mistake of writing the derivative of that in there. When you're doing the chain rule, you have to leave the inside stuff alone the first go around. Take the derivative of the outer function, which is being raised to the 9th power, and then multiply by the derivative of the inside stuff, which is going to be 6x squared plus negative sine of x. I'd probably write minus sine of x. Minus the derivative of cosecant is negative cosecant of x times cotangent of x. That's going to be positive cosecant of x times cotangent of x. Sure, fraction with chain rule. So do you mean I think I know what you mean, but I will guess what you mean, and then you can tell me if I'm right. So what I think you mean is something awful, which is fine, like this. The derivative of, let's not make it too crazy, James. Let's say it's sine of x over x squared plus cotangent of x. Sorry, not cotangent squared, just cotangent of x to the 6th power. Something like that. Well, I don't care if I'm right or I'm wrong. I mean, I do care, but we're going to do this one anyway. And then if that's not what you wanted, whoever the person is that texted me or chatted with me, let me know. We'll try and address what you want. So there's actually a couple different ways you can go about this. One way people sometimes do it, which I think is more work, is to distribute the power of 6. So you could write it, although I'm not going to write it, as the derivative of sine of x to the 6th power over x squared plus cotangent of x to the 6th power. That's a perfectly fine way of doing it. If you do it this way, you kind of have to use the quotient rule first and say, okay, it's the bottom times the derivative of the top, which you'll have to use the chain rule for, minus the top times the derivative of the bottom, which you'll have to use the chain rule for, all over the bottom squared. I would rather do the chain rule part kind of first. And I'm seeing this as, in fact, maybe I can even do both if you really want. Only if you really want, though. I'm seeing this as, okay, the derivative is, I've got some stuff, right? All of this stuff to the 6th power. And my derivative is going to be 6 times my stuff to the 5th power times the derivative of my stuff. So it's going to be 6 times sine of x over x squared plus cotangent of x to the 5th times the derivative of that, which I'm just going to write as the derivative of that, meaning I'm going to write sine of x over x squared plus cotangent of x prime. Meaning I have to write more, right? I'm not done, but I just want to point out, right? Here's my stuff that's being raised to the 5th power. And over here I'm multiplying by the derivative of that stuff. And then we actually have to do the derivative of that stuff using the quotient rule. So it's going to be 6 times sine of x over x squared plus cotangent x to the 5th times quotient rule time bottom derivative of the top minus top derivative of the bottom of the bottom squared. So it's the bottom. And since there's more than one piece, I'm going to put that in parentheses times the derivative of the top, which is cosine of x, minus the top, which is sine of x, times the derivative of the bottom, which is 2x minus cosecant squared x. All over the denominator squared. Kind of gross, but it is what it is. I definitely wouldn't simplify this unless I was specifically asked to. One thing people often do though is when you if you do multiply these fractions out, the top I'm not going to worry about. The top is going to be sine to the fifth times all of this garbage, which I'm just going to leave it as. But what I want to mention is that if you do multiply at the bottom is x squared plus cotangent to the fifth times x squared plus cotangent to the squared. So the bottom actually becomes a little bit nicer, and then it becomes x squared plus cotangent of x to the seventh power. So okay. I can do it this way if you want, but I'm only going to do it if someone asks me to. It's okay to ask. If you really want to see it, you should ask. But I would do it that way, obviously. I'm out of water. Oh, I can last the next 20 minutes. Okay. Let's see. Yeah, I want to go that way next. Oh, yeah, that's why I didn't do that. So the thing is, sure, that's the chain rule, or at least that's the, what's the word I'm looking for? This is the power rule version of the chain rule. But there is a more general version of the chain rule, which instead of saying, so here, the way I'm seeing this is, I've got some function to another function, right? And the way I take the derivative is I differentiate the outer function, I leave the inside alone, and I multiply by the derivative of the inside. I'm going to do the same thing, but I'm going to do it with a different function. Instead, I'm going to say, let's take the derivative of a composition of functions, which this also is. It's just this is a very specific type of composition. This is more general. And I'm going to do an example that I hopefully will help make it make sense. We're definitely not going to prove the chain rule because it's kind of complicated. But I'm going to show you an example to help you believe that it really does work. So, same idea. Derivative of f of g of x. I'm going to take the derivative of the outer function. So I'm going to get f prime of, I'm going to leave the insides alone, times the derivative of the insides. So I'm going to get f prime of some stuff times the derivative of that stuff. And I'm taking the derivative of f of some stuff. When I differentiate f of some stuff, I get f prime of the stuff times the derivative of the stuff. Here's an example that I think is helpful. Let's see. Yeah, I'm going to do it that way. Okay. So this is, I'm going to go back to, I'm going to go back to our graphing derivatives kind of days. I think someone asked me, I'm not positive, I think someone asked me about graphing the original function from the derivative. And I meant to do an example like that, but I have not come up with a good example, so I probably won't get to that. Sorry. Time is limited. But what I want to say is, I'm going to remind you guys that yes, we know the derivative of sine is cosine, and the derivative of cosine is negative sine. But we also talked about how you can see that graphically. And let me be very careful with my graphs here. So I'm going to draw the graph of sine. Try and draw it, and I'm also going to draw the graph of the derivative down here. Hopefully these come out pretty nice. And I guess I could use Desmos or something, but I feel like I'm trying to show something here that really kind of, the point is the graphing of it, not just seeing the graph. Okay, so we got our usual 0 to 2 pi. Pi over 4 is like pi over 2. Sure, that's like 1, 2. And negative 1, negative 2. Same deal down here. Okay. I'm going to graph sine and its derivative, and then I'm going to show you something else. So here's sine. So in blue, sine starts at the origin, then goes up to pi over 2 comma 1, then back to 0, then over to 3 pi over 2 negative 1, back to 2 pi. And we have definitely talked about graphing its derivative by finding the slopes of the tangent lines. Right? So in fact, look at this. Someone might ask you, oh, hey, where does sine have a horizontal tangent line? Well, we can just see graphically, if you look right here at pi over 2, sine of x has a horizontal tangent line at pi over 2 comma 1. Right? That's the point, pi over 2 comma 1. Which means that at x equals pi over 2, the derivative is 0. I'm going to draw the derivative down here. So pi over 2, the derivative is 0. And also at 3 pi over 2, right? At 3 pi over 2, I also have a horizontal tangent line. And so at 3 pi over 2, the derivative is also 0. And then it's not quite as precise, but I will tell you at y equals 0, the tangent line is the line y equals x, so the slope is 1. And over here, the tangent line has a slope of -1, and over here, the tangent line has a slope of +1. So it's -1 here, and +1 back over here. And not surprisingly, we get the cosine function, right? We knew the derivative of sine was cosine, so we're not surprised to say, oh yeah, the derivative of sine is cosine. And that looks pretty good. I mean, I've drawn better, but you know. All right, but here's what I really want you to see. So if you tune that part out, pay attention to this next part. I'm also going to do, let me draw this. So y prime is cosine. Okay, now I'm going to graph sine of 2x in red. A function of a function, a composition of functions, right? You can say, oh, this is my g of x, and sine is my f of whatever. So this is an f of g of x. And I would expect the derivative to be cosine of my stuff, right? The derivative of sine is cosine of stuff times the derivative of stuff is 2. So I would think the derivative is going to be cosine of 2x times 2 if the chain rule is true. Let's graph it. So sine of 2x, what does that 2 do to the period? It smushes it. It makes the period shorter by a factor of 2. So my period for sine of 2x is 2 pi divided by 2, which is just pi. So instead of getting a full cycle of sine from 0 to 2 pi, now I'm going to get a full cycle of sine from 0 to just pi. That means all of this motion has to happen in half the space. So I break that up into quarters. At pi over 4, I'm going to top out at 1. At pi over 2, I'm going to be back to 0. Oh, sorry, 0 is the start of 0. At 3 pi over 4, I'm going to go down to -1. And at pi, I'm going to be back to the order, to 0. I'm going to do a full period in just that 0 to pi space. And if I look at that, here's what I get. And I've drawn that, okay. And then it would repeat, right? So you'd actually get the same thing again. And you would get like that. Okay, so here's what I want you guys to see. I definitely get horizontal tangents at pi over 4 and 3 pi over 4. So in the same, from 0 to pi, at pi over 4 and 3 pi over 4, I'm going to get a horizontal tangent. So I'm going to get a 0 here and a 0 here for the derivative. But now I want to ask you guys, and this is kind of the important part, and I know it might be hard to see. What graph has a steeper tangent line at 0? The blue graph or the red graph? Which one is steeper? Blue or red?
The red.
The red one's steeper, which means it has a bigger derivative. So whatever the derivative here at 0, it's definitely bigger than 1. And I will tell you it is actually 2. So the slope here, right, the slope of this tangent line is 2, right? We're going over 1 and up 2-ish. The graph is not perfect. So that means the derivative is 2. And then the same thing over here. At this point here, the slope of the tangent line is -2. And then back over here, we're back to 2 again. So if you look at this graph, it's definitely a cosine graph, but it's smushed by a factor of 2 horizontally. So it is also not cosine of x, but it's cosine of 2x, right? Because the period is half of what it was. But the amplitude is also stretched out by a factor of 2. So you've got a 2 in front there. And that's exactly what we think the quotient rule, the chain rule would have made the derivative, right? The chain rule says, oh yeah, the derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. So the chain rule works, and it really works for any composition of functions. So let me actually write something down here because I think it's worthwhile. Yeah, I should take a moment to write this down. So, well, actually, let's do, yeah, we got that. Let's do a couple examples, and I'm going to write down kind of the rules you want to know. Yeah, I can, and then I'll probably also, yeah. So let's say our function was f of x is, I don't know, let's make it something crazy like tangent of x cubed plus 5x. So I know the derivative of tangent of x is secant squared of x. So the derivative tangent of some stuff is going to be secant squared of the stuff times the derivative of that stuff, which is 3x squared plus 5. You really do need those parentheses over there. If you write it without the parentheses there, it looks like it's secant squared of this times 3x squared plus 5. Whereas it's actually just to be secant squared of this times all of 3x squared plus 5. So make sure you use your parentheses liberally. Whenever you have something that you're multiplying by and it's got more than one term added or subtracted together, you probably should use parentheses. Or what if we had something like g of x equal to, yeah, let's do one of those. Let's do e to the x to the fourth plus sine of 2x. So we haven't done an e one before, but that's okay. So what's the derivative of e to the x? Oh, it's e to the x. So if the derivative of e to the x is e to the x, the derivative of e to the stuff is e to the stuff times what?
4x to the third plus cosine 2x.
You're mostly right. But what it really, yeah. But the answer, so yes, you're very right. The answer I'm generally hoping for though there is if I say e to the stuff times, all I really am looking for is the derivative of the stuff, right? Because that's always what we want to do. If you're doing the chain rule and you did the derivative as like outer function derivative to this with the stuff, you always have to multiply by, oh yes, the derivative of the stuff, which is exactly 4x cubed plus, now the derivative sine of 2x, we have to use the chain rule again. The derivative sine of 2x is cosine of 2x times the derivative of 2x, which is 2. And that 2 is only multiplying the cosine. It's not multiplying the 4x cubed. Okay. Yeah. So here's what I kind of want to say, and I'm gonna. So this is like, I don't know. There's actually still a lot of these things. Basically, I think about having a regular version and a chain rule version of each function in this derivative. So function derivative. I'm gonna make a quick list here. We know the derivative of e to the x is e to the x. Sine of x is cosine of x. Cosine of x is negative sine of x. Tangent of x is secant squared of x. What else? What else do I want? Secant of x, sure, is secant x, tangent x, and so on, right? Cotangent x is negative cosecant squared x. Cosecant x is negative cosecant x, cotangent x. All right, so, but we also can think of having a corresponding chain rule version. Well, if the derivative of e to the x is e to the x, I'm essentially going to take each of these and replace the x's with stuff. So the derivative of e to the x is e to the x, the derivative of e to the stuff has to be e to the stuff. What do I have to multiply by?
The derivative of the stuff.
Thank you, exactly, right? If ever I'm saying stuff, it's like, oh yeah, he means the derivative of the stuff. But right, that's the chain rule, right? We did the derivative of the outside function. We left the inside stuff alone, but then we have to multiply by the derivative of the stuff. So in fact, each of these lines is going to have a derivative of stuff at the end. So for the derivative of sine of x cosine x, the derivative of sine of stuff is cosine of the stuff times the derivative of stuff. Derivative cosine of stuff is negative sine of your stuff times the derivative of stuff. And so what I really want to say here is like, if you know your regular derivatives, and you should know them, you know your chain rule versions. You're just replacing every instance of x with stuff, and then at the end, you're multiplying by the derivative of stuff. That's why when I say, you know, what's the derivative of, you know, like something crazy like, I don't know, tangent of a bunch of garbage, I'm like, well, I know the derivative of tangent of x is secant squared of x. So I know the derivative of tangent of garbage is a secant squared of garbage times the derivative of the garbage. Right? I'm always relating the tangent of x, derivative of secant squared of x to tangent of stuff, replacing the x with stuff. So I'm replacing the x with stuff. The derivative is secant squared of stuff times the derivative of stuff. And I really want to write the next one down because the next one I feel like is one that really kind of throws people off often. So the derivative of secant of x is secant of x times tangent of x. The derivative of secant of stuff is not secant tangent of stuff. It is secant of stuff times tangent of stuff times the derivative of the stuff, which is kind of a lot to write. And I won't do the last two because I think you guys get the idea of it now. I also, yeah. So real quick, last example. If I wanted to, maybe two last examples. If I wanted to find the derivative of secant of x to the 6th plus e to the x minus sine of x, well, the derivative of secant of some stuff is secant of that stuff times tangent of that stuff times the derivative of the stuff, where the stuff is x to the 6th plus e to the x minus sine of x. Same stuff goes there. And then finally, I multiply by the derivative of the stuff, which is 6x to the 5th plus the derivative of e to the x is e to the x. And the derivative of sine of x is cosine, so minus cosine of x. That's how I do it. But people get thrown off by this because they're like, wait, the stuff comes up twice? Yeah, the stuff comes up twice. So if you're taking the derivative of secant of some stuff or cosecant of some stuff, you're going to get, if it's secant of stuff, tangent of stuff times the derivative of stuff. If it's cosecant, you're going to get negative cosecant of the stuff, cotangent of the stuff times the derivative of the stuff.